In this example, we'll be looking at a particle on an inclined plane, otherwise known as a slope. Here, the plane is inclined at 30 degrees to the horizontal. In this case, our particle has a weight force acting downwards. As the particle isn't sinking into the slope, we have a normal reaction force acting perpendicular to the slope. We'll call that R. In the examples we've seen so far, we've always chosen to resolve in a horizontal or a vertical direction. When working on an inclined plane, it's often simpler to choose two different perpendicular directions. One of those directions is parallel to the slope, and one of them is perpendicular to the slope. Let's consider the normal reaction force. We could extend the line of this force backwards, and that gives us a line that is perpendicular to the slope. What I'd like to do now is have a look at the properties of angles in these kind of diagrams. As the weight is vertical and this surface is horizontal, here we have a right angled triangle. That means if this angle down in the corner is 30, the angle in the other corner must be 60 degrees. And since we have a right angle here, on the other side we must have two angles that sum to 90 degrees, so the angle in here must be 30 degrees. And the key thing that I would like you to take away from this problem is that the angle at the bottom of the slope will always be the same as the angle between the weight force and a line that is perpendicular to the slope. And that will be useful when we want to work with components of the weight force in the directions that are perpendicular or parallel to the slope. Example 5. In this question, we're going to use g equals 10 meters per second squared. We have a box of mass 4 kilograms released from rest at the top of a rough plane, inclined at 30 degrees to the horizontal. The length of the plane is 120 meters and the box experiences a frictional force of 10 newtons. In part A, we need to calculate the normal reaction force between the block and the plane. Let's start by taking this diagram and annotating it to make it into a force diagram. Let's write in the mass of the box, 4 kilograms. And first of all, we'll add a weight force. So that will be 4g acting vertically downwards. The box isn't sinking into the slope, so we'll have a normal reaction force acting outwards, which we'll label R. Finally, we have a frictional force. The box is going to move down the slope, so our frictional force will be opposing motion and will work in the opposite direction, parallel to the slope. And the direction of acceleration will be down the slope. To find the normal reaction force, we're going to resolve perpendicular to the slope. So perpendicular to the slope, we have the force R. Going into the slope, we have a component of the weight force. Recall earlier that we said the angle at the bottom of the slope here is always going to be the same as the angle between the weight and the direction that's perpendicular to the slope. So we can add that onto our diagram here. So the component of the 4g force going into the slope is crossing the angle. So we'll have 4g cos 30. The block moves down the slope. It has no acceleration perpendicular to the slope, so this equals 0. Rearranging gives us R equals 4g cos 30. Putting this into our calculator gives us 34.6 newtons, but as we're using a value of g equal to 10, we need to round that to one significant figure. So R is 30 newtons to one significant figure. In part B, we need to calculate the time taken for the block to reach the bottom of the plane. In order to do that, we'll need a Suvat equation, but first we're going to calculate the value of A. Resolving parallel to the slope, taking downwards as the positive direction, we have a component of the 4g force acting parallel to the slope. We're not crossing the angle, so this time we'll have 4g sine 30. We have a resistive force of 10 newtons. And that's going to equal mass times acceleration for A. So A gives us 2.5 meters per second squared. Now that we've calculated a value of A, we can find the time taken. Recall we know the length of the plane is 120 meters, and we also know the particle is released from rest. So let's write down our SUVAT values. The length of the inclined plane is 120 meters. The particle starts from rest. We don't know the final velocity, but we do know the acceleration is 2.5 meters per second squared. And we're trying to find the time. So we need an equation that links S, U, A and T. The equation that we want is S equals UT plus half AT squared. Substituting in gives us 120 equals 0 plus 1/2 times 2.5 T squared. A half of 2.5 is 1.25. We'll divide through. That gives us T squared equals 96. Square rooting both sides gives us T equals 9.79, but since we need to round to one significant figure, we get 10 seconds. Right then, here's a similar problem for you to have a go at. Pause the video, have a go, and then come back and check your solution against mine. Okay, welcome back. Here's my solution then. First of all, in this question, we're using G equals 9.81 meters per second squared. That tells us answers need to be to 3 significant figures. We have a sledge of mass 12 kilograms being pulled up an inclined plane with an acceleration of 0.25 meters per second squared. Let's add that to the diagram. The plane is inclined at an angle of 32 degrees and motion is resisted by a frictional force of 30 newtons. In part A, we need to calculate the normal reaction force between the block and the plane. So first of all, let's add some forces to our diagram. We have a weight force acting vertically downwards of 12G. We have a normal reaction force acting out of the block, we'll label that R. And we have a frictional force resisting motion of 30 newtons. To find the normal reaction force, we resolve perpendicular to the slope. We have the normal reaction force coming out of the slope, and then the component of the weight going into the slope. Recall this angle here will be 32 degrees, and we're crossing that angle, so we'll get 12G cos 32. There's no acceleration into the slope, so that equals 0. So R will equal 12G cos 32, which if we put into our calculator, gives us 99.8 newtons to 3 sig fig. In part B, we need to calculate the tension in the rope pulling the sledge. So resolving parallel to the slope, as it's moving upwards, we'll take that as the positive direction. We've got the tension force going up the slope. We have 30 newtons coming down the slope. And we also have a component of the weight force going down the slope. We're not crossing the angle, so that will be 12G sine 32. That's going to equal mass times acceleration, which is 12 times 0.25. Let's rearrange to make T the subject. And then we can put that into our calculator, giving us a force of 95.4 newtons to 3 significant figures.